Hi, my name is Daniel Green. Today I'm going to tell you about signals of a quantum universe. This is based on work with Rafael Porto from a paper that appeared earlier this year. So the plan for the talk is first I'm going to introduce the problem of the origin of structure in the universe. Then we're going to talk about Bell's inequalities, in particular why it's difficult to implement them in cosmology. Then we'll discuss the signal of quantum mechanical origin of structure, and then talk about how non-local hidden variables theories could give similar results. Okay, structure of the universe. So when we look out on the universe on different scales, we see structures of various kinds. Nearby, we see stars and galaxies. But as we look out to the scale of the universe as a whole, we see the distribution of galaxies, or the cosmic microwave background, that are consistent with primordial density fluctuations that are very near scale invariant and Gaussian. The conventional picture of where this came from is one where inflation occurred long before the universe was reheated. And during that time, the universe expanded nearly exponentially. And the quantum mechanical fluctuations during that era were thought to give rise to the initial density perturbations. So the origin of structure in these models is typically one where the vacuum, being an interesting place in quantum field theory, has this dynamics that through the evolution of the universe, and particularly this exponential expansion, these vacuum fluctuations get stretched to the point that they become real physical fluctuations, classical fluctuations that we observe in the cosmic microwave background. Now, this is a compelling story. It is certainly consistent with observations, but more to the point, it's a kind of explanation that captures the imagination. So the simplest way to explain to a layperson why it's so exciting is that we have this connection between the largest objects in the universe, clusters of galaxies, and their origin comes from physics on the smallest possible scales, the quantum mechanics of fluctuations of the vacuum. And this is a beautiful idea, but we should actually worry that it's such a beautiful idea that we might not be thinking of whether the universe actually chose to work this way. In particular, this is similar to when people argue that free will is explained by quantum mechanics. And for this to really work, you really need to decide if that's really necessary to explain observations. In particular, when we look out at the universe on other scales, we see all kinds of structures that emerge from classical dynamics. Classical physics gives rise to all kinds of structures, the most common being just thermal fluctuations themselves. So if you take a gas at constant temperature, you'll see all kinds of structure emerge, and that's simply because of the thermal nature of the system. But even non-thermal systems that are complex often behave as though they're random, even though there's really some specific microscopic configuration. But due to the large number of particles, it's better approximated to treat it as a random system. And often in these examples, what's really going on is that when you have large numbers of objects, the central limit theorem gives you essentially universality, even if the individual pieces all are non-Gaussian or behave in some unusual way. Because of these facts that we know to be true about nature on other scales, it's natural to ask if we really know that the universe worked in this quantum mechanical way, or whether classical fluctuations could have equally given the universe we observe. Now, Bell gave us a way to test the quantum mechanical nature of ordinary states through the Bell inequalities. But what was different with Bell is that Bell gave us a recipe to determine whether a state we observe is quantum mechanical at the time we make our measurements. This is different than the universe because the universe we know is classical today, or when we make our observations. We're talking about big classical objects like a cluster of galaxies. To try to infer that it was quantum mechanical the way Bell does is impractical. What we actually care about is not whether it is quantum mechanical today, but whether quantum mechanics was important for the origin of these classical structures. Now, one could just imagine going in a time machine or effectively creating a model of inflation where one acts as a Bell measurement during inflation itself. But unfortunately, we don't actually know that, we don't have the luxury of doing that, nor could we be sure that a model of inflation where something like that happened was what described the world. Instead, what we want is some way to tell in a generic model of inflation without some highly tuned configurations. Okay, so now let's review how Bell works and why that's difficult to implement cosmologically. So what Bell's inequalities are really telling us is a reflection of the two kinds of probabilities that occur in the physical world. So the first is quantum probabilities, where different events are assigned a complex number, here's script A, and the probability of some final outcome is the absolute value squared of the sum of all of the possible ways in which we could have arrived at that configuration via these complex numbers. We contrast this with classical physics, where in classical physics, each event would be assigned a real number between 0 and 1, and the probability of something occurring is the sum of all of the individual probabilities. So these are just two different rules for probability. Now, even in quantum mechanics, if we only observe one number, so we're just asking about a single observable, we can always choose to diagonalize the problem. So we can always work in eigenstates of this observable such that, well, there's really just one complex number, and the absolute value squared of that complex number can be treated as a classical probability. However, in quantum mechanics, observables don't have to commute. And so if we were to do two different non-commuting measurements, we can't choose a basis that diagonalizes both at the same time. And this is the essence of what Bell's inequalities do. As an example, just to illustrate the diagonalization, for example, if we took a system where we represent the states in terms of energy eigenstates, we could treat the probability of finding any particular energy eigenstate as some classical probability. But now if we ask what is the probability of finding a particle in a certain position, given a superposition of energy eigenstates, we would get a bunch of interference terms that wouldn't have occurred if it was really a classical system. Another way to think about this is that the way we understand classical probability is that it's really a lack of knowledge of the microscopics of the system. In particular, that there are probabilities assigned to whole trajectories, and we don't know which one actually occurred, but once we make the measurement, we can really infer that what happened the whole way along was just one classical trajectory, and our uncertainty of the initial conditions, for example, is what is ultimately the origin of the statistics of the final outcome. But once you know the final outcome, you could really infer that the whole trajectory is what occurred. The same is true even in quantum mechanics in a certain sense if the observable commutes with a Hamiltonian. So if we're talking about some observable O that we could just, again, characterize the states in terms of eigenstates of that observable, then again, we can treat the final probability and the initial the final probability as just the absolute value squared of these individual amplitudes. But now we again have the freedom to make different observations at the final time, and we might say, well, I prepared the state in some energy in some eigenstates of O, but now I want to observe in the O prime basis that doesn't commute with O. And now here, when we make the measurement, we can no longer diagonalize the problem, and it really is true that we have to add up all of these complex numbers and take their absolute value squared. So this is the idea of why Bell's inequalities are true. But just to remind ourselves how it works in detail, the way that the simplest setup for explaining Bell is to take a system that splits into two parts. So we prepare a state, perhaps in a superposition or in a mixed state, and we separate them into two pieces. These two pieces are space-like separated, so the measurements on either one don't actually affect each other. And now we perform measurements either A or A prime or B and B prime in on those two states. Now, these measurements don't have to commute. So for example, if this was a spin, we take it to be, we could take it to be a measurement in the Z basis or measurement in the X basis. But all we're going to assume is that these are binary measurements. Sorry, I missed that. We're assuming that these return A prime, B, or B prime, return numbers that are either plus or minus 1. So regardless of whether we work in the A basis or the A prime basis, either way, we're going to get a number plus or minus 1 out of our measurement. Now we define some operator. We call it C, which is really just the possible measurements I could do. So it's a sum of the different measurements. I can measure in the A basis in one place, the B basis for the other one, A prime and B, A prime and B prime, and I construct this combination. And now we ask, what is the biggest possible number I could get from measuring, from statistically build up from measuring this quantity? Now, it turns out that this quantity is nice in that if I square it as an operator, the operator I get back is 4 plus the commutator of A and A prime, B and B prime. And it turns out that the largest possible number I can get from measuring C, which is just a combination of individual measurements on either side, is at most as big as C squared as an operator. So this is where we connect with Bell. Bell's inequality says in a classical probabilistic system, any local hidden variable theory, the largest possible number you can get for measuring this is 4, because this is a system, from classical mechanics is where these commutators vanish. And so the operator C squared is just the number 4. So the largest possible C I can get is 4. On the other hand, in quantum mechanics, the commutators don't vanish, or they don't have to vanish, more accurately. And so I can, if I pick A prime, B, and B prime appropriately, I can get a number bigger than 4, thus violating Bell's inequalities with quantum mechanics. But part of what makes this derivation particularly important is that we see the central role the non-zero commutator plays. And so what we really need is a non-zero commutator if we want to see the structure of quantum mechanics. This is essential because now we're going to come back to the problem in cosmology. And in cosmology, from various perspectives, one can see that the commutators just vanish like the volume of the universe. So the simplest one is just to say, if I take my adiabatic density perturbation zeta, and I look at its commutator with zeta dot, because these are the quantities I can imagine observing cosmologically, then diffeomorphism invariance is going to give me that I get a delta function divided by the square root of the determinant of the metric, which is a power of a cubed. And what this means is that the best case scenario for measuring these kinds of quantities is that I get a commutator that's suppressed by the volume of the universe. I say best case scenario because I haven't even taken into account decoherence, which would make this problem even harder. Instead, for all practical purposes, what I can observe cosmologically is really equal time correlators of one variable, zeta. Now, because I don't measure non-zero commutators, instead, these correlators are just taken with the absolute value squared of the wave function. And so for any practical purpose, I can just say that the absolute value squared of the wave function is a classical probability distribution, and it's completely equivalent to a classical problem. Okay, so now we want to see how we can circumvent this issue. Okay, so our only hope, so we've established that if I replace the absolute value squared of the wave function with a classical probability, I just call it a probability distribution, I can't take the probability distribution and claim that it is itself quantum mechanical. Instead, the idea we want to pursue is that the dynamics themselves, classical versus quantum, can give rise to different probability distributions. So said differently, this classical probability P that I got from squaring the wave function, the space of possible P's might be different than the space of probabilities that you can arrive to by classical dynamics under some set of assumptions. So our hope is that maybe if we understand how you generate or what kinds of probabilities you generate from quantum mechanics, we'll understand that those are a different space than the kinds of probabilities you get from classical mechanics. So as one simple illustration, the idea is now, imagine that my Hamiltonian does not commute with my observable. And our hope is that somehow the Hamiltonian itself is going to, that does the time evolution, will act as the Bell measurement. So I'm going to measure on a basis that doesn't commute with the evolution, and somehow that interplay will give rise to a set of probabilities for O that's not equivalent to a classical, the kinds of things I get from classical mechanics, because I can't diagonalize the whole problem. And so I can't treat this as just classical trajectories. Maldacena wrote down one model that implements this idea, although Baroque kind of shows in principle that it's possible. So the previous work that had been done for over many decades had focused on this idea, the way that we're going to tell the probability is by doing a literal Bell measurement at the reheating surface. And by this previous argument, it's easy to see that this always is suppressed by an enormous number. So what Maldacena did was to say, well, what if I take, it's suppressed by this enormous number at the reheating surface. What if I just move that Bell measurement back to the time of inflation? And by writing a sufficiently clever model, the dynamics of inflation effectively performs that Bell measurement and then stores that information in the mass of some particle that then gives rise to some hot and cold spots at the reheating surface. So what this does is it does the Bell measurement back when the commutators are non-zero and then stores it in a way that is not altered by later evolution. Now, the problem with this model is that there's no particular reason to think the universe evolved this way. It's literally a model designed to implement this Bell measurement. And furthermore, even if you sought this pattern of hot and cold spots, you would only know that it proved that it was evidence of a violation of Bell's inequality if you happen to know that this is the correct model of the universe. So, but in principle, it does show this idea that the dynamics themselves can implement the Bell measurement. And so this is what we want to see done in a more generic model. The idea that the other key idea we're going to use is that the difference between classical probability and quantum probability is really that classical probability is about one trajectory that really happening, and we're just uncertain of which one it is. And as a result, this means that the density perturbations were not just there, created at the time we observed them or created by the expansion of the universe, but were really always there. And we just didn't happen to know what the sign and what the phase of an amplitude of that particular density perturbation was as we trace it back to earlier times. As a result, these things are real. They're real since the moment they're created, and real fluctuations are sines and cosines in some, for some density perturbation. In contrast, quantum vacuum fluctuations really aren't real things until they're created. So they're created in the case of cosmology by the expansion of the universe, but prior to that, prior to horizon crossing, they're not really fundamentally there. Instead, the physical things are these positive, negative frequencies that tell you about whether you're excited above the vacuum or not. And this difference between sines and cosines versus positive and negative frequencies is really this key difference between the kinds of probabilities that define classical and quantum mechanics. So let's see how this works by just looking at a simple example producing Gaussian fluctuations. So we'll assume inflation is occurring throughout, and we'll work in the limit where it's exact de Sitter. It won't affect anything we're going to say. And so then we'll imagine the adiabatic density perturbations are produced by de Sitter mode functions plus with amplitudes that are given by A dagger and A. In quantum mechanics, these amplitudes are the creation and annihilation operators, and they obey the quantum mechanical statistics written here. So A dagger produces a state, a one particle state, and A annihilates the vacuum. As a result, you get this sort of quantum fluctuation out of it that there's a non-zero two-point function for these variables, but in only one ordering. The other one annihilates the vacuum, reflecting the non-zero commutator of the fields. In contrast, in classical physics, these A and A daggers are just statistical variables. They're classical statistical variables representing our uncertainty about the true amplitude of these fluctuations. So they obey classical statistics, where we've chosen the classical statistics here to reproduce the quantum mechanical answer. So in particular, we assign the two-point function this factor of 1/2, but because these things are classical variables, they commute. And so we get 1/2 in either configuration. Now, as I said, we chose this to reproduce the quantum mechanical answer. So either way, if I compute an equal time correlator in either the classical or quantum model, I'll reproduce the same two-point function for the fields. And in fact, since it's Gaussian, all endpoint functions will be the same. What this means, in particular, since observations effectively make an equal time measurement at the reheating surface, we will get the same observable quantity. So observations won't be different in the quantum and the classical case. Now, still, if you go and calculate a non-equal time correlator, you will find answers that are different. And this is a reflection of the fact that there's a non-zero commutator. And so the non-equal time is just the integral of some non-equal time commutator. So if we want to tell the difference, we're going to have to move beyond Gaussian fluctuations and move beyond Gaussian fluctuations and look at higher point correlators of non-Gaussian statistics. So here's where we have to make some kind of assumption, because again, if I just hand you the final probability distribution, I can always make it look classical. So what we need to do is make an assumption that we're going to make the assumption that there's some dynamical explanation for the non-Gaussianity we observe. So in particular, I'm not just allowed to put in the non-Gaussianity in the initial state of the system, like when the modes are well inside the horizon during inflation, but really that I want to explain the non-Gaussian correlators through dynamics during inflation. So in particular, that I assume that there's some local evolution during inflation that gives rise to this non-Gaussianity. Furthermore, our goal is to find some signature of the quantum nature of the state by finding something that doesn't depend on the details of the interaction. So not this, I invent an interaction that does a Bell measurement, but I write down an interaction that's fairly generic, and I ask, is there some feature of those interactions that can tell me the difference? And this final fact that I want something generic and I want something that has the feel of being common to all models is one key difference between the kinds of questions one would ask in cosmology versus the kind of questions one would ask in computing. Because the way you would show something works in a code to show that something really dependent on quantum mechanics would just be to implement some gate in the middle that implements a Bell measurement. And this would be sufficient to prove something about a computer, but not sufficient for the purpose of cosmology. So to see how this works, let's just start with a simple example, and we'll see how the generic outcome results later. So we'll pay, for algebraic convenience, we pick this cubic interaction, zeta dot cubed. The time derivative interaction is convenient for the algebra. A standard in calculation is given here and gives rise to the following three-point function for the adiabatic density perturbations. The thing to note here is the total energy pole. So in particular, there are two facts. The first is it goes like inverse powers of the individual k's in a product, so k1, k2, k3. But then this total energy pole is the sum of the norm of the vectors. So this is a sum of k1 plus k2 plus k3 to some power. Here in this particular interaction is a cubic power. This total energy pole is the cosmological, or more accurately, the in equivalent of the total energy delta function that would occur in scattering. So in a scattering experiment, you take a particle in the infinite past, and then you bring it in, it interacts, and it goes out to the infinite future. And because the timescales are infinitely long, we demand exact energy conservation. Or not we demand, we get exact energy conservation in flat space. Instead, if we're looking at these equal time correlators, or in cosmological correlators, we don't have these infinite times, and in particular, the uncertainty principle can produce particles from the vacuum. And so instead, this total energy pole corresponds to a suppression by the deviation from exact energy conservation to some power, which is typically an integer. Furthermore, the residue of this pole is the flat space S matrix in a particular limit. And so this fact is extremely important in showing why this is a generic outcome. So in particular, for any interaction, we'll always get these total energy poles from vacuum correlators. It just what goes on in the numerator is what tells you which kind of interaction it is. So the interactions determine the S matrix elements, but they don't determine the total energy pole. And again, this is exactly what would happen in scattering. It doesn't matter what kind of interactions you put in, you always get an energy conserving delta function, and it's the coefficient of the delta function that tells you which kind of interactions were involved. Okay, so now let's repeat this in the case of our classical model. So again, we're going to take the same interaction, but now the way we think about it in classical mechanics would just be to solve the equations of motion perturbatively. So we would move the interaction to the right-hand side of the equations of motion, treat it as a source at higher orders using the Green's function from the Gaussian theory. Now, when we do that, you recover the total energy pole in the three-point function, but now you find three new poles. And these are poles that arise at physical momenta, so I don't have to analytically continue to see the pole. I find the pole at reasonable momenta, and these correspond to poles in the so-called folded shape. So when the energy conserving delta functions form is the statement that the momenta form a triangle, or sorry, momentum conserving delta functions momenta form a triangle, and this folded shape is when the triangle is squashed. Now these poles correspond to another process we can think in terms of scattering. So in particular, if I had a particle in the initial state, and I had a cubic interaction that allowed it to decay, then this total energy, this energy conserving delta function for that process, decay of particles in the initial state, is now on shell. So it's possible for one massless particle to decay into two massless particles that are collinear. And the fact that this delta function can be, we can satisfy this delta function for physical energies is why we get these poles in correlators that can diverge for physical momenta. Now the fact that these poles arise is really a reflection of something about the S matrix again. So in flat space, again, the residues of these poles is really tied to the flat space S matrix. And we know the flat space S matrix that we have this so-called crossing symmetry that allows us to relate amplitudes in different configurations just by flipping the signs of energies. So in particular, when we look at the S matrix, we know that if we have an amplitude for 0 particles that go to 3 particles, then I have a related amplitude for 1 particle that goes to 2 particles, 2 to 1, and 3 to 0. And all of these are just related by flipping the signs of the energies that are involved in the process. The only difference now between these different processes is how many particles are in the initial state. And this is where classical mechanics really comes in, is that classical mechanics, there's no such thing as vacuum fluctuations in classical mechanics. There's always particles in the initial state classically. One way to see this is to note that our Gaussian model was really an independent amplitude for a sine or cosine. So what we're really producing are sines and cosines that are equal parts positive and negative energy modes. As a result, if you were to look at what the classical probabilities look like from a quantum mechanical perspective, they look like highly excited states. They look like states that are equal parts positive and negative energies, and nothing is annihilating the vacuum. And so there really are lots of particles in this state, which again is what you'd expect from classical mechanics, because in classical mechanics, empty space is a boring place, and there's nothing that can fluctuate there. Instead, these fluctuations are really there. There's really particles around. There's really these fluctuations around going all the way back. We're in an excited state from the very beginning, and all we're talking about is the evolution of these wavelengths of these individual fluctuations under the expansion of the universe and local interactions. And that's really the key difference with quantum mechanics. So in quantum mechanics, we really are talking about a state with no particles initially, and the particles are only being created through the expansion of the universe at horizon crossing. As a result, even though the crossing symmetry demands that all of these processes come together, the demand that we start in a state with 0 particles prevents the other terms from arising. So the absence of the 1 to 2, 2 to 1, and 3 to 0 processes is not something to do with the interactions, is not something to do with symmetries, but is a direct reflection that they were in the quantum mechanical vacuum. We can see this in more detail by trying to rewrite the quantum mechanical answer in a way that reflects the classical answer. So we can use the in formula sufficiently massaged to write it in a way that looks like this local Green's function acting on with the perturbation. And what one finds is that the in correlator can be rewritten in a way that looks just like the classical answer, except that the operator ordering of the individual terms is different. Using the commutator now to rewrite it so the operator ordering gives the same answer, we arrive at this formula that tells us that the difference between the quantum mechanical answer and the classical answer is really the product of commutators. So we really isolate that this has to do with quantum mechanics because it's really the non-zero commutator, which, as we've established, is really the fundamental thing that tells us that mechanics is that there's quantum mechanics in the universe. Equally important is that because commutators vanish outside the light cone in a relativistic system, and we're going to make observations at a time when all the individual points are space-like separated, we can trace back the origin of this difference to the mutual intersection of the past light cones. So not only is it measuring a non-zero commutator, it has to be measuring this non-zero commutator back at the time when the modes were inside the horizon and they were all still in constant contact with each other. And so we see that what this is doing is really implementing the idea, the sort of the essence of the Maldaceno's model, but now with generic interactions. So we're performing a measurement of a non-zero commutator back during inflation, and then that non-zero measurement is changing the statistics at later times, and we can't change the result again later by evolution outside the horizon, because the central result depends on the fact that these points, that this measurement occurred when these points were all in causal contact. So what are the observational implications? Well, the key difference here is the total energy pole versus these folded poles. So what the quantum mechanical signature corresponds to is to some equilateral amplitude. So some amplitude for equilateral non-Gaussianity. So if we have a model that generates equilateral non-Gaussianity, we will compare it to a classical model where if there's the same amplitude in the equilateral configuration, it would also have poles in the folded configuration. Now, these poles actually give rise to infinite signal to noise. And in real physical models, this pole is actually resolved into a bump. And so one source of that is already present in this model, which is the decay itself creates a finite width for the particle. So in real examples, when you include the width of the particle, which may come from resumming higher loop diagrams, like it does in flat space scattering, you can see that these poles at physical momenta get moved to complex momenta, but only slightly and proportional to the decay. Either way, one gets at least the same, if not higher, amplitude in these folded configurations and can be used to distinguish these two shapes. So the last thing we should look at is the role of locality and causality in the origin of this difference. So we know, even when Bell wrote his famous paper, it was David Bohm had already created a model of hidden variables that reproduced all of the results of quantum mechanics. And really, the key of understanding Bell is that Bell shows that a hidden variables theory that doesn't have long range it allows you to affect physics non-locally or violating locality or causality cannot violate Bell's inequalities. And so what we'd like to see is if our cosmological signal has that same character to it. So let's just see if we can build, if we abandon trying to really write down a dynamical theory and just write down something that in principle looks like classical mechanics, can we arrive at the same conclusion? So here we'll be inspired by the relationship between positive and negative frequencies and our final result. So what we want to do is we want to write a classical theory that somehow picks out only the positive frequencies, which was really the key in the technical detail in getting only the total energy poles. So total energy poles meant you were only integrating about where the sign of the complex exponentials were all the same. So to do that, what we'll do is we'll write a complex scalar field, but we'll again give it classical statistics. But now with a complex scalar field, the positive and negative frequencies are really different objects. So we have A and A, so we have A dagger and B for phi. And what we'll do is we'll only give the positive frequency a classical fluctuation, and we'll just turn off the negative frequency. Then we'll just invent a Green's function. So we'll just declare we have some Green's function. We won't claim to give a mechanical model for it, but we'll just write one down that inspired by classical mechanics. We'll declare that the nonlinear correction to the field, this complex field evolution, is the same as what you get from this kind of cubic interaction if we replace the classical Green's function with this object, which propagates only one preferred sign of the modes. This interaction, what this looks like is one real particle decaying into two antiparticles. When we do this, we get, because we've always been careful to only pick out the one type of mode, we'll get the total energy pole and no additional poles. And this again is consistent. We've created net creation of three antiparticles, just like we have produced these, our quantum mechanics model produces three particles from nothing. Now we can see the connection to locality as follows. So if we just take our Green's function, so the Green's function we've used for propagating information, and we look at the limit where we take both times to 0, so the future infinity on the reheating surface, and this corresponds to the propagation of information from 2 points on the reheating surface. Now, all of these points are space-like separated, but yet this propagator we've chosen still is non-analytic in K, which means that it has non-vanishing support at every point along the reheating surface. So in this particular case, it corresponds to 1 over x squared propagator between points that are space-like separated. In contrast, a local theory that really respects Lorentz invariance and locality, that commutator has to be a delta function, because these points are space-like separated, and therefore the only non-zero commutator should be when the points are coincident. If we wanted to implement that kind of propagator, then we're forced to put back the negative frequency mode. So we put in, instead of a single sign exponential, we really need that exponential to go to 0 such that we reproduce this delta function, which requires that this thing is a sign. Now when we put this into our model, we pick up one of these negative frequency poles. Or we pick up one of these negative frequencies, which corresponds to the pole in the folded limit. And physically what this is corresponding to is that there's an additional process where 2 particles come in and annihilate, producing 1 antiparticle. And what we're seeing here is the relationship between this crossing symmetry, this fact that I have to have all possible versions of the amplitude together, not just 0 to 3, but 2 to 1, 1 to 2, etc., and causality of the system. That the reason I have to have those things come together is because the system should obey these general principles of causality. And the way to see that in a picture is as follows. So imagine I have this real particle that can decay to 2 antiparticles. Then because of the uncertainty principle, I can never be sure that one of those particles didn't decay outside the light cone. There's always some probability that if I were to set up my detector, I would find that there's a non-zero probability my antiparticle that I measure in this decay is outside of the light cone of the decay itself. And this, again, is a reflection of the uncertainty principle that I can never exactly localize the particles. Now, when I boost that system, we'll find that there's an equivalent process where, because this particle is outside the light cone, when I perform a boost, it can change the ordering in time. So now this thing that looks like a decay now looks like a particle coming in and hitting the initial particle, producing one antiparticle. And this relationship, this is the reflection of why we need antiparticles. This is exactly the argument that antiparticles are needed to implement causality. And it's the same argument that tells us that we have a decay process. We also have to have this annihilation process. And so Lorentz invariance tells us that this combination coming together is one that we don't have any control over. Okay, so to summarize, what we found is that the presence of a total energy pole and only a total energy pole is a generic feature of non-Gaussianity in the quantum mechanical vacuum. This total energy pole is a reflection of the energy conserving delta function. In quantum mechanics, this is the only pole, but in classical mechanics, this pole comes with other poles corresponding to the presence of particles in the initial state, where the energy conserving delta function is a reflection of the fact that one particle can decay to two particles while conserving energy. This doesn't happen in quantum vacuum fluctuations because there's no particles in the initial state. This fact that these extra poles come together is a reflection of locality, and this is why it can be avoided in non-local hidden variable series. Thank you.